So charge amplifiers are another type of circuits wherein which again the concentration is on improving the input impedance such that there are no loading effects on either the sensor circuit or on the next stage, usually that is a analog to digital converter stage. So by improving input impedance and reducing the output impedance, we can achieve this. So in an effort to do so, the charge amplifiers are designed. The name actually charge amplifier means it doesn't amplify the charges. Keep that in mind. It is not amplifying the charges. In op-amp circuits, we don't have any facility to amplify any electrical parameter. It only amplifies the difference voltage which is available at the two difference input ends. So here basically what is done in charge amplifiers is even current amplification is also not possible. We are converting current to voltage and that voltage signal is getting amplified. So basically all the op-amp circuits are voltage amplifiers. So whatever input or whatever the sensor measurements we want to amplify, we have to convert them to their proportional voltage readings. And then those voltages should be applied to the difference input terminals. Only those will be amplified. Now here charge amplifier means basically an amplifier circuit as usual using op-amp whose equivalent input impedance is not resistive type. Usually it is the case in all the op-amp circuits, but here it is consciously made to be capacitance. So by connecting a additional capacitance at the input terminals, it is seen to it that the input impedance is not resistive, but it is capacitive. And this is capacitive at especially the lower frequencies, it offers very high input impedance. And our aim in designing these charge amplifiers is basically to not lose out on the low frequency signals or even DC signals, because all our self-generating amplifiers, self-generating transducers or sensors are, the outputs are DC most of the time. And even if they are AC, in case of your piezoelectric sensors, where the output is invariably AC, which is current, not voltage. So for specially such sensors, where the output is a slow value or a very small value of current, in case of piezoelectric sensors, always for current output, you can take piezoelectric sensor as the standard. And also, another disadvantage of these piezoelectric sensors is not only the output is current, but also the circuit provides very high output impedance. The piezoelectric sensor provides very high output impedance. As a result of this, that impedance has to be properly balanced. Otherwise, the current, whatever we get out of it, is going to be even lesser than actually what is being sensed. So first thing, it is a current output device and it is low frequency AC signal. Plus the output impedance of the piezoelectric sensors is very, very high. So these are the three factors. In spite of piezoelectric sensor being very sensitive and very good for many applications, these three have to be properly matched, or these three parameters have to be properly taken care of to sense accurately the piezoelectric sensor readings. Similarly, there are a good number of sensors which fall in this category. So we'll stick on to this piezoelectric sensor example so that equivalent circuit also is very easy to draw. So here, first thing, low frequencies. For low frequencies, the amplifier should provide very high input impedance. Next thing. So How exactly it functions? So whatever the current is available out of the sensor, that current is applied to a capacitor. And definitely it is a low frequency signal. So AC signal, when it is applied to a capacitor, this capacitor naturally charges proportional to the current coming. Now these charges definitely develop a potential across them. This potential is applied to the difference input terminals of the op-amp. Like this, the charges are converted to proportional voltage with the help of an additional input capacitance, which helps in improving the input impedance parameter of the overall amplifier. At the same time, the output impedance is also reduced by connecting another capacitor in the feedback path, and in the diagram it is shown as C0. So a pure capacitance is connected as the feedback element. So by doing this, the output impedance is reduced to few ohms. So our aim in designing a good amplifier is achieved here, and this helps at lower frequency signals, or for the measurement of lower frequency signals and amplification of lower frequency signal. This circuit helps. So a simple capacitance which is connected here, which helps in measuring the current, which is converted to voltages or charges first, and these charges develop the potential difference, and this potential difference is amplified. This is how a simple charge amplifier works. It is not simply charges to voltage conversion. Please understand this. Now, what is the role of these different capacitors? The input capacitance which is connected, okay, that is to improve the input impedance and making it purely capacitive. The effective input impedance is going to be capacitive by connecting like this. Now, this C0 is the feedback element, and similar to all our feedback amplifiers so far whatever we have studied, accordingly this feedback element helps in feeding the output to the input to the negative terminal. So for negative feedback it helps. Now you can see here final output voltage available here is Qs divided by C0 plus C plus C0 divided by AD, which is similar to our regular R plus R1 plus R2, where R1 is the input resistance and R2 is the feedback resistance, and R2 by R1 with the minus sign is the inverting gain of the amplifier. Here also in this case also it is the same. Only thing it is in terms of the capacitors, and when these capacitors are connected in parallel, the effective capacitance is equal to C0 plus C. When they are connected in series, the effective capacitance is 1 by C effective is equal to 1 by C plus 1 by C0. So here you can see in this AD is the difference gain of the amplifier. This equation we get it by considering offset DC offset 0, input offset current 0, plus the cable and the sensor resistors are all properly matched. Considering cable resistance to be 0, that is ideal cable and an ideal sensor whose impedance is properly matched. So considering these factors, this equation we get. But practically, this is not so. Now, practically, what is the situation? You can see here in this. Practically, you have this sensor connected here. From out of the sensor, there is a resistance of the sensor, the output resistance of the sensor. plus the capacitance of the sensor. Similarly, there is a cable connection from the sensor to the input terminal of the op-amp. So cable also has got some resistance, plus cable with casing, shielding, it forms some effective capacitance, say C suffix C, and then our usual input resistance and input capacitance of the op-amp. So all of them are going to be appearing like this. If you draw the equivalent circuit of this, considering the practical conditions, this is the ideal condition. And considering the practical conditions, if you draw the equivalent circuit, it looks somewhat like this. Now, what is going to be the effective capacitance available at the input? C1 plus Cc plus Cs is the total capacitance available here. All of them are connected in parallel. So, total effective capacitance available at the input terminals is going to be equal to Cs plus Cc plus C1, where Cs is the sensor capacitance, Cc is the casing or the cable capacitance, and C1 is the input capacitance which is connected at the input terminals of the charge amplifier. Similarly, the total resistance is going to be, or the effective resistance is going to be Rs parallel Rc parallel R1. Because they are in parallel and connected to the same ground. Considering again what? The shielding, ground are all proper and the voltage levels are maintained at the same potential. There is no disturbance in these voltages or the ground or the reference voltages where the shielding, ground or all these potentials are connected. All these elements are connected. So assuming these things, now if you have a DC offset of VIO as usual due to the input offset current IIO, then what is going to be the final output? On which parameters the final output is going to be considered? Here, just see here, this is nearly equal to QS by C naught. Now, where the AD is gone? Because AD is very, very higher than 1, because it is the difference gain. So, it is of the order of 10 to the power of 6. So, this parameter becomes negligible. C plus C naught, these are simple small capacitance, even if it is in the order of microfarads or so. But AD gain is too high. So, this is going to result in a fraction which is much, much lesser than 1. So, here this is nearly equal to QS by C naught. Why nearly equal to is, in some cases, if it is a considerable quantity, then the effect of that has to be considered while calculating the V naught. Because when sensitive measurements are involved, sometimes these also may have certain effects and you may have to provide some compensating network, or you may have to design some networks where this term has to be taken care of. This may give substantial voltages, or it may reduce the voltage here, the final output voltage. So, it has to be taken care of. That's why it is nearly equal to QS by C. So, to some extent, the charge amplifier described in the earlier case is certainly ideal because we have omitted sensor, cable leakage resistance and input amplifier input resistance. So, the practical circuit what we have shown here is the one which we considered just now. Now, when we consider here, this circuit is assuming that VIO and IIO are 0. Suppose they are also included in the circuit, because naturally when we use op amps, there is always this VIO existing. Either that has to be calibrated properly or reduced to zero, or some compensation network has to be provided there. If that is not done, then at any point of time, because it is a temperature varying factor, it may drift. So care has to be taken here, or the calculations have to be made to considering these VIO and IIO factors. Now, when you consider them, naturally what is done is, here we add to this saturation effect has to be first thing nullified. Otherwise, here this is an open loop gain. So these things get amplified to a very large extent. So what is done is a C0 feedback along with another resistance R0 is connected. Now by doing this, what are we going to achieve? Here, this is a regular circuit. Now what we are doing is we are considering for our analysis even the offset currents as well. That is IN and IP are the offset currents. And due to which this is the VIO, that is the input offset voltage generated at this. So naturally all of these voltages and the voltage across this effective capacitance is going to appear here. Now what is the impact of this? Now earlier also we have seen, to reduce this impact, there is a resistive network designed here such that this offset voltage and along with the voltage what is coming here at the inverting terminal, they get added up, because this is a minus voltage, this is another plus voltage proportional to this, that is IP current is generated, and these two get added up such that the effective VIO is reduced to 0. So that the effect of input DC offset voltage is equal to 0. And now whatever the charges equivalent to this, what voltage is getting produced, that is available, and this gets amplified and available at the output. Now what is going to be your final output equation if this is the with the compensating network? So R0, which is the feedback resistance connected in parallel with C0, also affects the contribution of VIO and IIO to the output. If RP is the parallel resistance, which is R parallel R0. R is what? The effective resistance of all the parallel combinations. If that is taken care of, then your output voltage VO is going to be equal to input offset voltage plus at the positive, that is at the non-inverting terminal, whatever is there. So this in turn gets reduced to a very small value, and 1 plus R0 by R is the final output voltage. If this amount is negligible, then whatever is the output available here will be due to the gain of this. So whatever input comes in, so that will be the final output. So here the errors are continuously like this, minimized or reduced or kept small. Error must be kept small enough not to reduce the output dynamic range. So here you can see there is a capacitance and resistance parallel combination RP and CP, which is connected to the non-inverting terminal. This even in trans impedance amplifier also we have seen, or auto zero amplifier also we have come across this kind of arrangement where a specific resistive network is designed such a way that R1 plus whatever is the feedback resistance, that is R dash whatever we had developed, that and this RP which is connected here to the non-inverting terminal are properly matched such that the voltage which is coming in here is balancing the VIO. This is to reduce the offset error. Now R0 must be as small as possible for the minimal frequency to be measured. Now here these resistive networks which are designed have to be designed in such a way that each one we know is going to contribute to noise. Each one is going to contribute to some power dissipation. And each of the resistor is going to be self-heated, and because of that the resistance is going to be varying or drifting with the temperature. So these three parameters, the drift, the power dissipation or the self-heating, all these three parameters have to be properly managed by providing shielding, grounding, or keeping them at proper distances from other heating element, such that the overall range of the measurements is not affected. So because of this, R naught must be as small as possible, because if R naught is more, then the power dissipated will be more. And also the effective impedance, our aim is to keep the effective impedance capacitive, so that may get hampered if R naught is more. Usually a resistor is placed shunting C naught rather than relying on the leakage resistance of the capacitor. The capacitors, how much ever ideal we consider them, they do have some leakage resistance. But in some cases, the leakage resistance are minimized to reduce the other effects of connecting the capacitors. Additional additional parallel resistance R naught is connected in parallel with the C naught. So given that R is mainly determined by sensor leakage, for quad sensors, R naught is chosen to be between 10. See, what is this G standing for? What is 10 to the power of 9? So this resistance value is chosen such that 10 to the power of 9 to 10 to the power of 12 with C naught, which is in parallel. Here, two circuits are shown with piezoelectric sensors. Now, this is the effective piezoelectric sensor circuit. This is the sensor. CS gives you the piezoelectric sensor effective capacitance. And one more circuit where this R1 is the protective resistance to the sensor. So the effective piezoelectric sensor impedance is capacitive, which is high in nature. And this is basically a current generator. So here you are showing it with a simple capacitance. Sometimes the crystal is also shown. In some circuit, I will show you. So the effective circuit, there are two circuits depending upon how much is the impedance of this and what is the current specification of the sensor. You can connect it either like this directly to the op amp, or you can connect it with a protective resistance like this, a series resistance R1 like this. So the high frequency response of charge amplifiers is limited by AD. Why it is limited by AD is because AD is the difference gain which is dependent upon the frequency. So at high frequencies, so the transfer function of the entire charge amplifier is given by this. This is high frequency. This is the frequency at which the amplifier is functioning, F. And C naught is that capacitance which is connected in the feedback path. And because it is in the non-inverting mode, so the transfer function ratio, it is output to the input charges. QS is the charges present on the input capacitance. So this transfer function is given by this formula, 1 by C naught. So C naught is very, very important here. The value what you choose for this feedback capacitance is very, very important. And also it plays an important role in reducing the output impedance as well. So where Fh is equal to Ft divided by 1 plus C by C naught. So these are the factors which are known. Any frequency, operating frequency. So small C naught, you can see here C naught in the denominator. So small value of C naught improves the sensitivity but also reduces the bandwidth. So there is a trade-off between these two. Whenever you want larger bandwidth, appropriate value of C naught should be chosen. Whenever you are concentrating more on the sensitivity issue, then C naught should be small. If you want larger bandwidth, go for higher C naught. If you want higher sensitivity but bandwidth doesn't matter, even if smaller bandwidth is okay. If your operating range is small, then you can go ahead with smaller bandwidth. So under such cases, you can choose C naught value appropriately. Adding a resistor in this range. With op amp inverting input here, the resistor values and the wattage rating is also mentioned because the power dissipation is an important parameter. So here our aim is to improve the stability and at lower frequencies also the charge amplifier should provide high input impedance and low output impedance along with other parameters which we considered in trans impedance and auto zero amplifier designs. That is the offset requirements, DC offset currents and voltages plus the gain factor and also the input impedance parameter. So considering them, a charge amplifier like this is designed.